We're going to take a look at question 11.1, which is the first question in the steady flow energy section of the FEEG1003 thermofluids workbook. So steady flow energy equation, a few things to note. It usually involves air, enthalpy, usually compression, and in this case you can see that we've got a gas turbine which has a compressor in it. And the questions are usually quite wordy. So rather than 3 or 4 lines of text and a couple of variables or parameters, we've got an awful lot of information in the question. But actually, this question is quite guided in the way it's written. So actually, it's not really that difficult. So we have a standard gas turbine. Fuel is mixed with air, which is then compressed. Or compressed air and fuel are mixed together. Then spark type ignition, combusted. The gas rapidly, the chemical energy turns into heat, so it rapidly expands, increases in temperature. It's passed through a turbine, which spins a shaft onto a generator. So very, very simple. So we'll start with a question. So we've got an industrial gas turbine engine. First part of the question, atmospheric air, so at temperature 15 degrees. Remember, translate all of these temperatures into degrees Kelvin. Flows with negligible kinetic energy. So when you look at the steady flow energy equation, it's quite long. So there's obviously no kinetic term, no potential term in this either, we can assume, because there's nothing about levels. So you can quite soon see that the heat and work process for this application just can be based on the enthalpy of the gas. So we have a flow rate here, mass flow rate of 316 kilograms per second, a pressure, and some more temperatures, and a duct area. So the minute I see mass flow and duct area, so an area and a mass flow, it means we might be asked to find something like a velocity or a volumetric or mass flow rate later on. So first part of the question, part 1 of part A, is use the equation of state. So PV equals MRT, or P over rho equals RT, and the mass flow rate relationship at state 2 to find the mean velocity. So there we go straight away. We've got a duct area, we've got mass flow rate, so it's quite simple to then find the mean velocity of the air. And then it says use the steady flow energy equation, so we're going to simplify that right down, find the power, so the work, basically mechanical work required to drive the compressor, and then in this case noting that the exit kinetic energy cannot be neglected. So we're going to do it 2 ways, including and excluding the kinetic energy. Second part B, first it starts off with a statement that we can ignore the mass flow rate of the fuel. So again, we're just modeling now the combustion in terms of the air, which is a really, really simple process. So we're going to have to find the heat basically, which will be some function of the change in enthalpy. So again, you should, when you see that on the board, you see it's a very, very simple arrangement, chopped down version of the steady flow energy equation. What's next? Okay, so the part B is the heat. Part C, calculate shaft power. So now we're working, so in part A we've worked out the work in. In part C we've got to work out the shaft power, so the shaft out, power out of the engine. Again, neglecting or not the kinetic energy. And then finally work out the this is where we work out the work out and then the efficiency, which is the network divided by the heat in. So for the network, we need to find work out minus in, divide that by the heat in, and then we find our efficiency value. Okay, so quite a long question in terms of words, but actually really quite simple, and the question really does step you through the different parts of the question. So we'll go over to the board now and we'll quickly run through this one. Right, so we've got air being pulled in from the atmosphere and it goes through a compressor. So state 1 is coming into the compressor, so at 15 degrees or 288 degrees Kelvin, and presumably at a pressure of 1 bar, 1 atmosphere. And the exit conditions is what we're concerned with. So we've got a pressure out of 12.56 times atmospheric. Got temperature out as we compress the air, it's increased in temperature as well. So it means we've got to put some mechanical work in. Okay, so work's going in, so negative sign in this part of the jet engine. And we're asked to find the mass flow out of the compressor. So not the mass flow, we've got the mass flow. We're asked to find the velocity out, okay? So that means we can start off by using the equation of state. So previously, in other parts of this module, you're used to this expression. PV equals mRT. That's where m is the mass. This is the big version of the equation. So m is mass in kilograms, and r is equal to 287 things. Okay, and that value of r doesn't change. We can rewrite this because obviously this is a compressor now, so we're compressing the air. So generally for the steady flow energy equation, we modify this so we can bring the m down. Now V over m has units of meters cubed per kilogram. We invert that, we get the density. So you can rewrite this as P over rho equals RT. So we can write that for state 2 coming out, so the exit of our compressor. So we do that and substitute in the numbers. So we've got P2, we've got R 287 things, and we've got T out as 668 degrees Kelvin. Okay, always transfer it into Kelvin. It's just best practice, even when you're looking at a delta value of temperature, because every so often you're going to get caught out and be asked to work out the properties of state of something, and you'll work it out in degrees Celsius rather than Kelvin. So we work out for this value of rho 2, we get 6.55 kilograms per meter cubed, which looks about right. If you look at the compression ratio, in terms of the differential pressures in and out, it's reasonably high, and standard density of air is about 1.23 kilograms per meter cubed. So this is a reasonable amount more. If it was less than that, less than 1.23, I know I've gone hideously wrong somewhere. Okay, so as I've always said, you can start to learn to appreciate the sign and the magnitude of your answer to see if you're in the right sort of ballpark. Okay, find the velocity out. We've got the mass flow, we've been given the area, we've also got the density. You can combine them all up and you should be able to rearrange them to find an expression for the velocity. Okay, where V is velocity, or if you're unhappy with that, we can write that instead, okay, because velocity doesn't start with a U. This is has the same dimensions either side, so kilograms per second. If you equate the units or dimensions on either side of that equal sign, they are the same. Not necessarily an equation you need to remember, but this goes back to your dimensional analysis that you did at the start of this module that you probably have horrific nightmares about. This is kind of what it's useful for, appreciating units and dimensions and making them equal. Okay, so we can rearrange this. We've got the mass flow rate, we've got rho 2, we've got A as 0.4 meters squared, I believe, or the diameter somewhere. No, it is 0.4 meters squared. So we can plug in all those numbers to find U. So rearrange this for U, and U equals 120.6 meters per second, which is quite a rocking value, quite large. Okay, so we found the velocity out U2. Okay, the next part asks you to work out the work in, so work done on the gas, using the steady flow energy equation. Now, you're used to the steady flow energy equation being Q dot minus W dot equals, and then the sigma function of out, and the three different things, and then minus sigma function of in, three different things. Okay. With the steady flow energy equation, when these sort of problems, we apply it to a very, very small block within a larger thing. So that steady flow energy equation simplifies massively. Okay, so for the second part, we can simply write this minus W, because it's working, it's negative. Working is negative, we want to minimise that, it's useless to us. We want to maximise the work out, minimise the work in for our highest efficiencies. And that's all we have. So we've ignored that there's no gravitational potential component. So the GZ disappears. And then usually in here we'd have U squared over 2 somewhere. But that's disappeared as well, because we've been told we can neglect the kinetic energy output. So it just simplifies to this, basically. So the work that we put in, done on the gas, equals the mass flow rate times the change in enthalpy. And we know that this change in enthalpy, this part here, is equal to Cp delta T, so from previously in the module. Okay, so really simple. So the work done on the gas is just the change we've made to its enthalpy. So stick the numbers in, 316, which is our mass flow rate, times Cp 1004, and then our delta T, which is 668. That equals minus 120 megawatts. Now, if we want to add in the kinetic component, we're just going to write m dot, so is it 120.6 squared over 2. Okay, so this is our kinetic energy. So 316 times that gives us 2.3 megawatts. So actually it's only 2% of the answer. So that's often the reason why we can neglect things like kinetic energy. If we're doing a lot of work on the gas in terms of changing its enthalpy, either through a work input or heat input, quite often that amount of work or heat is massive in terms of the total energy. So it's by far the largest proportion. So actually any kinetic energy in or out is actually really quite low. It's always useful to do a check though, and just make sure. But so 2.3 megawatts, so only 2%. Okay, so now we found the first part. We found the work in for our jet engine, and now we're going to look at the heat and then the work out to complete the question. Right, finishing off this question is it's a fairly quick affair. I've drawn block diagram of the combustor here, and then the final part, which is the turbine. So we've already worked out or calculated the work in. So minus 120.6 megawatts. That's the work gone in, mechanical work in to compress the gas. We're now going to work out the heat. Again, so the steady flow energy, again, there's no kinetic energy here, no potential, so the steady flow energy equation gets hacked to pieces and dramatically shortened. So we can just write heat in is the mass flow rate times multiplied by the difference in enthalpy. and obviously this equals Cp times delta T. So we've got T3, which is given in the question. Again, convert it into degrees Kelvin. So 1435. So we can write this out in full now. So 316 times 1004, 1435 minus 668. So 243.3 megawatts of heat. Okay, now moving on to the expansion of the gas. So this is where we get the work out. Again, we're going to neglect kinetic energy. You can go back through like we did in part A and work out the kinetic energy and then see if it is going to be significant in our answer or not. But for this point on the board, I'm going to neglect it once again. Okay, so this time no heat involved, just work process. So again, no potential term, we're going to neglect the kinetic term. Now, in terms of the steady flow energy equation, you obviously know it's Q minus W equals. So the convention would say we put a minus sign there. Again, it is convention. Common sense will tell you at the end that our answer is not going to be a negative amount of work. So exactly the same again, it's just the change in enthalpy, so the change in the differential temperatures. Cp is a constant. So 316 times 1004. And this time, again in Kelvin, 795 minus T3. So working that out gives us an answer of 203 megawatts. Okay, finally, just to work out the efficiency. Remember the work in and the work out, regardless of their sign, we're going to take the differential of the absolute values for obvious reasons. So work net equals 203 minus 121, roughly, that we have in part A. And therefore the efficiency equals 203 minus 121 divided by the heat in, 243. And that gives us an overall efficiency of 33.7%, so 34%. Now in the UK, to give you a bit of background, in the UK, well, in a lot of places, we used to have power stations that were exactly this, an open cycle gas turbine. So we draw in atmospheric air, compress it down, mix it with the fuel, spark ignition, it went bang, expand out, and then we realised some work from that. The efficiency, 34%, you think, well, gas is nice and hot, surely we get a better efficiency. The problem with these is that the exit temperature is very high. So 795, 800 degrees Kelvin, that's 550 degrees Celsius. But what we can do with that heat that's come out now, so it's exited, so we've got our work out, we've got gas flying out of here at 800 degrees Kelvin. We can then put that through what we call a Rankine cycle. So this is like what a coal-fired station would use. So we can use that to heat water in a boiler, create steam, and then the steam, we get work out from that. So the steam expands out, and then we get a second bite, so we have a second cycle. So we have power stations in the UK and around the world that are called combined cycle. and they use gas as a fuel. So the gas comes in, we have a standard Brayton type jet engine cycle, and then with the waste heat we put that through a Rankine cycle. So they have two linked cycles together. So the Rankine cycle, so the Brayton cycle on its own is quite low efficiency, but then you double that up with a second bite of the cherry, so you get another cycle on here, and the combined station efficiencies for these types of installations about 66 or 67%. So the nearest one to us here in University of Southampton is in Marchwood, over the other side of, just opposite the port. It's an 800 megawatt power station. It was constructed inside a year, very, very quickly, and it has a station efficiency of about that. Compare that to standard Rankine cycle. So the best coal-fired stations are about 35% efficiency, and the best nuclear sites about that or slightly lower, so about 33-35%. And these are the ones that again just use a standard single cycle, whereby either coal is fired in a boiler or you have nuclear fission, nuclear fission, and then that heats water in a boiler, creates superheated steam, and it's just a single type cycle. You might pass the steam through and reheat it and things like that, but you still just kind of have effectively a pseudo single cycle. So that's why combined cycle gas turbines, or CCGT, as their acronym goes, are very, very efficient. Gas is a fairly clean burning fuel. It has half the carbon intensity of coal. So that's why when the coal price went up in the 1980s, a lot of governments, especially in the UK, switched from coal straight to gas because your station efficiency is almost twice as much. Okay, so that's a bit of an extra bit at the end just to explain to you about sort of power generation and why this value is not too low. It's fairly standard because with these sort of cycles the exit temperature is very high. Okay, so that's question 11.1, the first question from the study flow energy section of the workbook for FEEG1003, the mighty thermal fluids module.